Okay, welcome back, everybody. Sorry I can't give you a image of me, but I have the camera used to show my work. So what a crazy week. I'm glad you're all doing okay and safe. Sounds like everyone is hunkered down at home. Got a bunch of new ice in Gresham. That's what I was told. And that's why we're not in today. So this is statics, and this is my book. Chapter 2 is what we want to continue on in. We did components last time, and I believe that's in chapter 2, components of a force, after they define forces. And the sign convention, there we go. We did components. So the next step after components is the addition of vectors. So I believe in chapter 2, oh, nope, that must be in chapter 3, because chapter 2 ends with just the rectangular component of a force. So anyway, I'm going to move on to chapter 3 and probably give you an assignment out of chapter 2, but working towards chapter 3. So yeah, we'll do some of these. It'll be decent practice. But then chapter 3 starts into the resultant of two concurrent forces. So that's adding vectors together. So this is pretty big because we need to know the total resultant of all the vectors. So if you have two vectors, typically you can create a triangle from the two vectors, or you can do it the rectangular component method. So I'm going to show you both. The rectangular component method sums up the X and Y effects, kind of like we did in class. But the rectangular method, or the triangular method, is you can create a triangle from two forces. So here's the two forces, the 100 pounds and the 140 pounds. And essentially, you take this vector, add it over here, tip to tail, and you make a triangle. This is going to create a non-right triangle. So then you'll have to use those strategies to solve it. You can only do this with two vectors. If you have three vectors, obviously you can't add three things together and make a triangle. So they go through a couple example problems for you on this. Here it is. Like I said before, we're going to put those vectors together tip to tail. We're going to keep them in their angular position. That is super important. And then the resultant comes from the start point and goes to the end of the second vector. Going to create a triangle, typically not a right triangle. So you'll have to, again, use your non-right triangle strategies. So there are a few good examples in the chapter for you to look at, but I thought I'd just make one up and go through it with you. So, and this is resultant of two concurrent forces. So let's talk about concurrent and non-concurrent, because that's something you're going to have to be aware of. Let's see, where's my visualizer? There it is. So hopefully you all can see that because I am screen sharing. Concurrent just means that all of the vectors come from the same point. So if we had three vectors and they're all coming from the same point, then this is known as a concurrent force system. Okay, now if we have, let's say, a beam, and this is the other kind of problem we're going to work with, and we have some support, and then we have some load out here, right? I'll put a distribution on. Clearly, all of these forces do not go through one point. So this is non-concurrent. two different strategies. So this is what we're going to do first, concurrent system. This is what we'll do second. This will be probably chapter 4, I would guess. But we use different strategies for a non-concurrent than we do for a concurrent force system. Again, most of the time is we want to find the resultant. And the resultant is the single force that can replace the existing forces on a force system. So we can turn all this into one vector, and we can turn all this into one vector. The book really breaks this into small pieces, and the first one is concurrent. Not just concurrent, but two forces that are concurrent. So when you have two forces that are concurrent, I'll give us an easy one here. We'll say this is 50 newtons, and we'll say this is 60 newtons, and we'll put an angle of 45 degrees. Okay? So, concurrent force system, a two-force system, these two can be added together, tip to tail. So I basically keep this at a 45, transfer it over. I'm going to draw it a little longer. 60 newtons, right? But this angle is 45. And then the resultant comes from the start point, because this is now kind of gone. I just added them tip to tail. Comes from the start point and goes to the finish of that second vector. And this is what we call R, the resultant. So it's a non-right triangle. We know that this is 50, this is 60, this is 45 degrees. Usually you want to make your picture pretty big when you're working these kind of problems. This 45 is not going to help me anymore because it was to this, right? But I know this now, don't I? The straight line is 180. So 180 minus 45 is, really don't want to do anything in my head. 135. So this angle C equals 135 degrees. And I end up with a side angle side situation, right? And this is R. So side angle side should trigger the cosine law. So that's going to be R. This is opposite, right? So I'm calling the hypotenuse R squared equals the two sides, 50 newtons squared plus 60 newtons squared minus 2, 50 newtons, 60 newtons, cosine 135 degrees. And that will give me R. All right. So with an HP, you kind of just work through the equation. You go 50 squared. It's totally different than a TI. So if this is going to mess you up, don't watch it. 60 squared. And then I can add those two together. So that's that function. And then I'm going to go to, so I enter that, which it doesn't then do anything to it. 50 times 60 times 135 cosine times, and then subtract it, and then that's this whole side, and then I want to take the square root of it. 101.69877 newtons. Okay, so that gives the magnitude. Now, if the problem said find the magnitude of the resultant, that you'd be done, right? But most of the time, we want to know the angle or the direction of the vector. That's one of the characteristics, right? So I know that it's R. I know it's at point A, so R coming out of A. So I know the magnitude. I know the location, point of application. I know the sense right here, but what I don't know is the direction or the angle that it acts on. So to get the full answer, you'd want to do another calculation to get this angle. So I'd do the sine law, and I'd say my resultant 101.69, and I'm just going to put dots, meaning that I will carry this over the sine of 135. So that's these two. Then I can use the 60 newtons over the sine of, I'll call it A, because I have point A there, right? And that should give me the angle in which R is acting on. So whoops, I already have that number stored. That's good. 135 sine divide. So that's this side, that number, right? So then I want to take 60 and divide by that number because these two are just going to swap places. So I'll put 60 in, and then I'll take that number and divide it. And then I'll take the inverse sine. So angle A equals 24.66 degrees. And that does make sense. It looks pretty small, definitely smaller than 45. So then I would write that like this, with this being my little indicator and 24.66 degrees, right? And then I would do the rounding here. So, all right. So that is two forces that are concurrent, triangle method, right? The component method would just say, hey, let's find the x of the 50, right? So we can say, well, I know Rx is going to equal, so that's the x component of this creature, right? It's going to equal the component of the 50 plus the component of the 60. So I can find those two components. So it's going to be the f, and I'll write it fx of the 50 plus the fx of the 60. And that's going to equal the x of the resultant, right? And then I would do the same thing and say, oh, the fy of the 50, which is 0, right? There is no y to the 50. And then it would be minus, because this is down, the fy of the 60. So that's going to give you the components of this creature, and then you just Pythagorean theorem out, and you have the rectangular component method of adding vectors. All right, so that's good enough. Let's give you some practice on that over the weekend, and that'll kind of keep us moving forward, and then we'll do, again, more new stuff on Monday. So let's see what we want to do here, if I can find some problems. And then I'll put this up on Blackboard so you'll be able to see it. It's a big chapter, so we do a lot of stuff in chapter 3. All right, so this first section is this component one. So let's do 3-1. I don't think we need to do a lot of them. And 3-3. 3-1 and 3-3. Okay? And I will put that up in Blackboard. And let's get that done for Monday so we can check it over and make sure there's no problems and then move forward. 3.1 and 3.3. Hey, everybody, have a great weekend. Stay safe. And sorry about all this closing shenanigans, but, you know, it is what it is. So we will see you on Monday.